If you have ever spent time near a small airport, you know the sound of a standard piston airplane, a low, rhythmic, sputtering rumble. But occasionally, an airplane with propellers will taxi by producing the distinct, high-pitched whine of a commercial airliner. It is a striking contrast that leaves many people wondering why some propeller planes sound exactly like jets. Before we peek under the engine cover to see why, make sure to like this video and subscribe to the channel. We are here to help you navigate your ground school studies and ensure you never miss an aviation lesson. This engine operates as a two-part team. You have a powerful jet engine core generating massive rotational energy, and it is paired with a traditional propeller that uses all that twisting energy to bite into the air and pull the airplane forward. Internally, the core of a turboprop, the gas generator, functions exactly like the giant jet engines you see on passenger airliners. It breathes in outside air, squeezes it down tightly, and ignites it with fuel to create a continuous, roaring fire. On a standard passenger jet, that fire shoots straight out the back to provide thrust. But a turboprop features extra, specialized turbine blades sitting right in the path of that fire. Their entire job is to capture that energy and redirect it forward toward the propeller. By combining these elements, a turboprop gives pilots the reliability of a modern jet engine while maintaining the efficiency of a propeller at lower altitudes and slower speeds. To see how this power is managed, we can look at the four major assemblies that make up a typical turboprop engine. The first piece is the power section. This is the primary gas generator that takes in air, ignites fuel, and creates the expanding gas that provides all the raw energy for the aircraft. But this creates a mechanical challenge. That jet core is spinning at tens of thousands of revolutions per minute. If you attached a propeller directly to something spinning that fast, the tips of the blades would break the sound barrier, and the propeller would likely shatter. To solve this, the engine uses a reduction gearbox. Think of this like putting a car transmission into first gear. It takes the extremely fast spin of the jet core and steps it down, turning that speed into a slower, incredibly strong twisting force that the propeller can actually handle. To keep everything running smoothly, the torque meter measures how much twisting force is being sent to the propeller, so the pilot can monitor engine performance. Nearby, the accessory drive uses the engine's rotation to spin the internal pumps and generators that provide the plane with its electricity and hydraulic pressure. Without the reduction gearbox translating that raw speed into strength, the power of the gas generator would be completely unusable. With the speed managed, we have to look at how that twisting force actually travels from the fiery jet core up to the gearbox. In aviation, there are two primary ways to make that connection. The first is the fixed turbine design. As you can see here, a solid metal shaft physically locks the rear turbine wheel and the propeller together. It works like a bicycle chain connecting your pedals directly to the back tire. They are physically linked and must spin as one. The second design is the free turbine. In this setup, there is no mechanical link connecting the jet core to the propeller at all. There is no shaft or physical connection joining the two halves of the engine. You can visualize this using two desk fans. Imagine two fans facing each other, but only one is plugged in. When you turn the first fan on, it blows a strong breeze into the blades of the second fan, forcing the second fan to spin even though the two machines never touch. A free turbine engine uses that air link. The jet core blows high-velocity exhaust gases across a completely separate set of blades, the free turbine, which then captures that wind to spin the propeller. If that two-fan analogy helps you visualize how the air link works, leave a like and let us know in the comments if you've ever flown on a free turbine aircraft. While the aircraft's design determines which system is used, both are effective ways of capturing the energy of exhaust gas to do physical work. Now that we know how the turbines capture the energy from the gas, we have to look at what happens to that air once it finally exits the back of the engine. A pure jet engine uses all of its exhaust to push the airplane forward, like a rocket. A turboprop, however, has already forced that air to do a lot of work spinning those internal turbines, which drains away most of its energy. This comparison shows the result. In a pure jet, the energy blasts out the back as thrust. But in a turboprop, the power is routed forward to the blades, leaving only a tiny amount of energy to exit the rear. This proves that the giant propeller is doing the actual heavy lifting for the aircraft. You now understand the core of the turboprop. It relies on a high-speed gas core to create energy, a specialized turbine to capture it, and a gearbox to translate that power into propeller rotation. Mastering aviation isn't about memorizing complex manuals. It is about understanding these mechanical concepts so you can feel confident every time you pre-flight an aircraft. If this lesson helped you, subscribe and share this video with your fellow students. We will see you in the next lesson.